Good morning, Astronomy 1010. Welcome to our second to last or penultimate week of lecture. This week, we're going to finish planetary atmospheres, go into the beginning of our lecture on the Jovian planets, which will carry over into next week. The class is coming to an end quickly, and that means we have to think about me catching up on grading and you guys catching up on any back homeworks that you have, provided they're not too far back. I can horse trade with you a little if you have a good excuse. But I want to clean it all up this week so that our final week of lecture is not messy. To that effect, I'm planning on canceling lab today. I had an experimental lab planned anyways, but it's not completely necessary. And I have one more lab that I want to do with you on measuring the mass of Jupiter. And I figured we can do that one next Monday. That'll be our final lab. So if anyone has any objections, or do you guys have any objections to me canceling lab today? No. I have some other important work that I need to do today, so it'll be nice for me to free up some time. And I especially need to finally get completely caught up in both of my classes. I made a big dent in it last night, and today I'm going to fix it. All right. So that'll make sure that we're all caught up, both you and I. Maybe use this time to try to finish one of your more recent labs or homeworks if you haven't turned them in, and turn them in before I closed out the submissions, okay? Okay, so today will be easy and breezy, and we'll continue to learn about planetary atmospheres. I also feel that I should mention there's some sort of big news in today's planetary science world. I don't know if you guys saw, but today we conducted our first successful atmospheric flight on another planet. They actually flew the Mars Ingenuity helicopter for the first time. And I woke up to that in today's Washington Post. If you guys would like to read about it, they even have a little video. Washington, it was the front page of all the major newspapers. So you can tell that's a pretty important science result. Here it goes. Sorry, you guys are blocking it. NASA flies a helicopter on Mars. Hold on, let me get rid of the ads. Excuse me. NASA flies a helicopter on Mars. First time an aircraft is flown on another planet. So it reached an altitude of 10 feet in what they called a Wright brothers moment. Now, here's the thing about this. As they mentioned in the article, you guys remember that Mars has a very thin atmosphere. It's roughly 1% the density of the atmosphere of Earth at sea level. So that means the rotors on the helicopters have to work a lot harder. Oh, damn it. Get out of here. Okay, there we go. We've had enough of that. Okay, so you can see it's quite difficult. The video isn't that that's stellar anyways, but they do show a little I don't think that this is a full video. I think it's a time-lapse photograph. Let's see if I can get that here of the helicopter starting up its propeller, getting about 10 feet up in the air, and then after proving that it can fly through the air, landing back down. So it was a sort of humble first space flight, but usually they kind of want to test these things out slow and steady, and they probably didn't want to go up too high, because if something did go wrong, if they lost aerodynamic lift, if the thing's going to crash, they'd rather have it crash from 10 feet than 30 feet or 50 feet, right? But I'm sure in no time that thing is going to be propelling all around the atmosphere of Mars. And that's nice because it can kind of quickly fly over craters and potentially identify spots where there might have been liquid water in the past, places for that rover to then head to and drill for signs of life. So I don't know, something cool related to planetary atmospheres. That's what we're talking about. I thought I'd share that with you guys. I've got my planetary atmospheres lecture up, and today we're going to talk about the sources and losses of atmospheres, and then get into some of the nitty-gritty about atmospheric gases, kind of cover some of those formulas that we learned in our last class. Oh, by the way, I should also mention that we need to be considering the final exam, You guys remember that we talked last week about potentially letting you guys skip the final and use your midterm grade in place of the final to free up some psychic energy. Is everyone still feeling pretty good about that? I know there are a few people out there that want to know the details of their grade first before they choose, and I'm working to get you those details. So if I owe you an email, stay tuned. That's what canceling today's lab is all about, is giving me lots and lots of time to clean this up. But it sounds like everyone's pretty on program with this. Let me just do two more little things. I'm going to hide the non-video participants. Sorry, Ryan. And then we're going to get into it. So let's start off with a picture of the atmospheres that we are considering. And let me ask you guys, if we consider the atmospheres of Venus, Earth, and Mars, and we want to talk today about where atmospheres come from, what's sort of the number one place where planets get their planetary atmospheres from? If I asked you that as a test question, what would the answer be?
Volcanism.
That's right, Ryan. So you've been with me, you're paying attention. Volcanoes create atmospheres. But Ryan, there's actually other ways to create atmospheres besides volcanism. And I want to show you one of my favorite weird moons in the solar system. I'm going to try to show you guys as much pretty pictures as I can today. But first, let's take a look at a little diagram that we might want to take some notes on, okay? Where do we get atmospheres from? Volcanism is obviously the number one place, but there are other ways too. Now, the book mentions bombardment by solar wind or small micrometeorites. In particular, in this case, they're thinking about the planet Mercury. On the planet Mercury, small collisions between solar wind ions and the surface kick off sodium atoms, which bounce around the surface of Mercury. And some people claim this is Mercury's atmosphere. Whatever. Couple of sodium atoms bouncing around a planet don't make an atmosphere to me. You know what I'm saying? Okay. So, however, this is a serious issue on Mars and on many other weird, strange worlds in our solar system that you don't know about. Evaporation is when you have some type of lake or liquid that turns into a gas. And do you guys remember what sublimation is? I told you this once before. What's the difference between evaporation and sublimation?
Is sublimation a solid to a gas?
Exactly. Very good. And remember, Jenna, that this will, of course, be an issue on worlds in which there is no atmosphere already present. And I'll explain that in just a moment. As an example of you seeing sublimation at some point in your life, let's consider frozen carbon dioxide. Remember that carbon dioxide is one of the primary gases that we see in a planetary atmosphere. I don't know if you've ever made dry ice cream or played with fog machines before, but here's some dry ice, some frozen CO2. Notice it's white color. And you can see it's undergoing at room temperatures and pressures sublimation. CO2 is so volatile that even under the Earth's atmospheric pressure, it skips the liquid phase and goes directly to a gas. Where would this be important? Let me show you a beautiful picture of Mars's ice caps. In particular, I'd like to show you this beautiful place on Mars called the Chasma Boreal. So the Chasma Boreal is a canyon in Mars's North Pole. And you can see here that it's a mixture of frozen water ice. So Mars doesn't have any liquid water on the surface today, but it has a lot of water ice. The ice caps are roughly half water ice, and the other half is dry CO2. And what we see happening on the surface of Mars is the water and the dry ice undergo sublimation, depending on whether it's Mars's summer or winter time. And this canyon grows or recedes depending upon how warm the temperatures are. And this sublimation actually contributes quite a bit to Mars's atmosphere. You can see there are some very beautiful images. I could only imagine what it would be like to travel on a little dune buggy through this terrain or to take a hike through these ice caps. It must be a very beautiful place. Um, although we don't have quite as many images as of in situ measurements from the poles as we do from the equatorial regions. So this is one place where we would see sublimate. Oh, by the way, let me show you another place on Mars that I love very much. The Noctis Labyrinthus. Okay, I want to show you two different pictures of the Noctis Labyrinthus. So first of all, at the tip of the uh, Valles Marineris is a set of Indiana Jones-like channels called the Noctis Labyrinthus. And you can see it here. Here's a reasonably high resolution image. And let's see if you can test your planetary geology skills. You're seeing a network of channels and caverns here, or basically, some canyons. What sort of geology does this look like to you? Let me see if we can find an even better picture.
I would say maybe erosion.
Erosion turns out to be pretty good.
My second guess was plate tectonics.
Yeah, I think it's probably some combo of that. You'll notice that it was really close, Jenna, to the Tharsis. Well, you might not have noticed it. I'm not sure if you did. Looking for that high color image here. So Noctis Labyrinthus is located right at the tip of the Valles Marineris. But notice in this picture, it's quite close to the Tharsis Montes bulge where all those big volcanoes were. You'll also remember that was a convection hotspot where underlying mantle convection was probably adding a lot of stress to your planetary lithosphere. So probably at some point, this started to fracture and actually stress out the crust. But eventually, like the canyon itself, it did become more of an erosional feature. Wait, I got to get rid of that red mark here. It became more of an erosional feature, and I want to show you some more examples of sublimation. Here's a picture from Viking 1. Can you guys see how the channels are all full of these giant, billowy, fluffy white clouds? That's all carbon dioxide that has sublimated into a gas and is now blowing around through the channels. And we believe that what's happened over the hundreds of millions of years, or maybe even a billion years, well, it's probably not a billion years old, but it's probably in the last billion years, after the canyons started to form, CO2 sublimates into a gas and blows through the channels, adding wind erosion and carving out the channels even wider than they would have been originally. But think about what you're looking at, guys. This is probably the solar system's greatest fog machine show, okay? Like, if you could walk through those canyons, it would be like Indiana Jones meets, the Pink Floyd Laser Light Show or something, because you'd be walking through these billowy clouds of CO2 fog. It would probably be pretty creepy to travel through there during one of those periods in which the CO2 sublimated. There is one really beautiful picture I was looking for, of the Noctis Labyrinthus, and I'm going to give it one more shot. I have it saved somewhere, but basically this last picture shows some of the frozen CO2. So here actually is a high resolution image. You can see that red Martian sand mixed in with deposits of frozen carbon dioxide. Kind of actually a beautiful image. It almost looks like some abstract art painting or something. There's one other picture of the frozen CO2 in the channels that I have always really loved. And it's pretty high res. I'm not sure why it's not the first one, because it's usually the best. Let me try one other thing here. Like I said, I always save these images, but I save them in so many different repositories that I always forget to call them up before class. Here it is. This is what I wanted. This is one of my favorite pictures of the Noctis Labyrinthus. And what I love about it is because the frozen CO2 deposits, because that dry ice covers the surface like frost, you can really see the contrast between the canyons and the surrounding highlands. So I just, I think this is quite beautiful. Let me show you another place in the solar system where we have cool sublimation at work. This week, we're going to try to transition to the outer solar system, past the asteroid belt. And you're going to discover that things get really weird when you go past the asteroid belt, because you cross this invisible barrier in the solar system that we call the frost line. And that's where a bunch of other types of gases start to freeze. Uh, Actually, let's have a test here. There's evaporation and sublimation, right? You guys know what the opposite of evaporation is when you go from a gas to a liquid, right? What's that called?
Condensation?
Very good. Now, this one you probably won't know, Jenna. There's a special term for when you go from a gas back to a solid. It's like condensation, but for solids.
Gas to a solid. Yeah, I don't know that one.
It's called deposition, like a deposit. Okay. I I didn't know that until recently myself, so don't feel too bad. Deposition. In the outer solar system, when we cross the frost line, we find certain gases freezing and sublimating at some sort of wacky cold temperatures. There's a moon of Saturn I love called Iapetus, and I wanted to share this one with you. It's probably one of the most exotic looking moons in the solar system. Of course, Google's new image share sucks, so okay, here we go. Look at the surface of this. Let's play planetary geologist. So far, you've been doing pretty good, Jenna. Clearly, this is a pretty extreme looking surface. They call it one of the highest contrast bodies in the solar system because of its dark side on the right and the white side on the left. All of that white stuff that you're seeing there is frozen water, okay? Is this a youngish surface or an oldish surface?
It's not young in a sense, but it doesn't look extremely old. There
Yeah,
are some impact cratering, but it's not an overabundance.
and what's interesting about these impacts, they don't look so fresh, do they? They look like something's happened to them. What does it look like? This is a massive impact crater, by the way. Impacts of this size that become a certain percentage of your diameter might have threatened to actually shatter this moon into a bunch of snowflake shards, okay? But in any case, what's up with the rim of this crater? What does it look like has happened to it?
It's been filled in a little by volcanism.
It's not volcanism because we can't see any volcanoes here.
It's been like eroded down.
Yes, it's been eroded. Here's the wacky thing, Jenna. How the hell can we have erosion when this moon has no atmosphere?
Is it from deposition?
Okay, sort of, but try the other version. Try the other way.
I'm forgetting the word. We just said it.
From solid to gas.
A sublimation.
Sublimation. Let's think about what happened. By the way, do you see this dark surface here? This dark surface, I believe, is the forward. So as a moon goes around a planet, right? If it's tidally locked, it has a forward pointing direction and a trailing direction, right? But I believe that dark surface is in the forward pointing direction, the direction that it's going, circling around Saturn, sort of maybe in the direction of the sun. The idea is that solar wind and solar radiation heat up the water into a gas. The gas becomes a mini temporary atmosphere of sorts. It blows across the surface of the moon in this direction. As it blows across the surface of the moon, it creates wind erosion, chipping away at the craters. And then the water then freezes on the backside and deposits into ice. But what happens is there's little teeny bits of dirt and grit in the water that kind of gets left behind when it evaporates. And that actually makes the surface darker. which changes the albedo. What's the albedo again? Remind me about albedos for a second.
That how much light is absorbed?
Exactly. And once it's darker, Jenna, is it going to absorb more or less light?
More.
And that's going to make the surface even warmer, correct? Which
Yep.
leads to more sublimation, which leads to more wind blowing across the surface, which erodes the craters even more, which makes it darker, and it becomes a positive feedback loop. So over hundreds of millions of years, this thing's left with all the gick on one side of it, a beautiful set of wind erosion, and then the deposits are on the other side, and you get this lovely two-tone surface. Very cool science that explains this. Another nice thing is it shows you that even in the absence of an atmosphere, surfaces can show evidence of wind erosion because of temporary atmospheres. I call this type of erosion frost jets to remind us that they start off as ice, they turn into gas, and they deposit. So let's do it's always good to take some notes before we get too carried away in our lecture here. Here we go. All right. So let's talk about, sorry, this marker is not as good as I thought it was. Sources of atmospheres. Number one source, volcanism. Number two source is evaporation or sublimation, okay? And if you need, oops, let me go into a large scale screen here. If you guys need the notes here, you can remind yourself that evaporation is liquid to gas. Sublimation is ice to gas, okay? Number three, which we're going to put in parentheses, micrometeorite bombardment. I guess you could have a large bombardment that creates a little bit of atmosphere. But I don't think that's common in the solar system. Well, actually, there is a small tenuous atmosphere around a moon of Jupiter that has solar wind causing its atmosphere. But we'll put it in there for completeness. Micrometeorite or solar wind bombardment. Okay, so that means there's just a few ways to gain an atmosphere. Unfortunately, there's a lot of ways to lose an atmosphere. Let's take a look at that note. Okay, let's think about the different ways that we can lose an atmosphere, and let's talk about two of them that are going to take a little bit to explain. Both solar wind stripping and thermal escape cause gases to bleed away out into outer space. And I'm going to want to say quite a bit about each of these things, okay? Condensation or deposition is where atmospheres condense or freeze out. We saw that on Iapetus. We haven't talked too much about this, but chemical reactions with the surface materials is a big explanation of how Mars got its surface turning so red, is because of its primordial oxygen mixed in with water, rusting the surface of the entire planet. And then you can definitely blast away atmospheres with giant impacts, all right? So I want to label all of these, and then we want to spend some time talking about the big picture. Basically, the story is that atmospheres are constantly being leaked away into outer space. Atmospheres need to be replenished, no matter how big your planet is. The reason why Earth has a healthy atmosphere today is because volcanoes are constantly erupting on Earth and adding more atmospheric gas. That compensates for the small leakage that we have into outer space. Venus must have some type of atmospheric gas. Must have some type of outgassing, some kind of active volcanism, or it wouldn't be able to maintain that thick atmosphere in the presence of the solar wind. Mars, on the other hand, its volcanoes have gone dormant hundreds of millions of years ago. And what do we see happening to the atmosphere of Mars today? It's thinning the hell out to where it has only 1% of the gas that Earth does. Most of its Mars at some point will lose probably most of its atmospheric gas. All right, let's talk about it. So losses of atmosphere. First of all, we have, how do I want to label these? Let's do some stars, okay? So something called thermal escape. We're going to have a discussion about this because it's not easy to explain. High speed gases in the exosphere of a planet. Remember that the exosphere is the uppermost layer of Earth's atmosphere. It's also the name for the uppermost layer of any planet's atmosphere. We'll call it leak into space. Remember that during our homework last week, we have a test for atmospheric loss, and that's to compare the thermal speed of the gases, which I should probably redefine for you. Is the thermal speed greater than 1/5 of the escape velocity? That's the condition for planets to start leaking their atmosphere and losing it over time into space. Solar wind stripping. This is sort of like thermal escape, except thermal escape happens whether you're in the presence of the solar wind or not. But solar wind ions, protons and electrons from the sun, slam into atmospheric gas particles at high speeds. They break them into smaller gas constituents, which can then achieve thermal escape. So solar wind ions smash gas molecules I'm going to say something that isn't quite grammatical, heating them into space, okay? I'm intentionally saying that awkwardly so that you'll think about the fact that heating leads to higher velocities and that causes them to leave into space. So that's a kind of weird thing to say, but it's not wrong. There's condensation and there's deposition. You might want to give yourself some reminder notes there. Condensation is gas to a liquid. When it rains on Earth, that's an example. Snowing could be an example of deposition. Gas to ice, okay? Or gas to a solid, I suppose I should say. An important one on Mars is chemical reactions. An example of which is O2 rusting the surface of Mars until the entire planet becomes red. And I'll tell you the story about that in a few moments. And then, of course, we can always have impact cratering. Let's not say cratering, but let's say bombardment, impact bombardment. So it looks like there's more ways to lose an atmosphere than there is to gain one. That's a troubling thought, since we sort of depend on atmospheres for our survival. I want to go through some science on these two. Okay. Let's talk about thermal escape. Here's an important note. Gas molecules move with a, and here's a keyword or phrase, a distribution of speeds. Put that in quotation marks because that's the sort of thing a science person would say. The gas molecules move with a distribution of speeds described by a Maxwell Boltzmann velocity distribution. Now that's a jargony sort of thing to say, but we need to understand it. I explained this to you during our homeworks, but this is the kind of thing you kind of need to hear a couple of times. Let's take a look at that cool animated Java app that I have. Oh, wow. Look at my atmosphere is still percolating away since the last time I pumped it up. Let's clear it out a bit so that you guys can sort of get a good look. Let's open this up. Let's keep lots of gravity. Let's do a light species and see what happens. Boom. I want you to take a look at them gas particles there. You can see that there's a little bit of thermal escape kind of going on. This might be the exosphere of a planet, right? Down here might be the troposphere of a planet. The gas particles are not all traveling at the same rate. And if I chill this thing down a little bit, you'll get to see that as we slow the speeds down, you'll kind of see that they're not all traveling at the same rate. Let's reduce gravity a little bit. Okay. Some of the particles are moving fast. Some of them are moving slow. Some are moving kind of in between. When you look at the gas particles with your eyeballs, it's not so easy to kind of add up what percentage is moving fast, what percentage is moving slow, and what percentage is moving medium. But it's not evenly distributed. This is a scientific measurement. You actually have to measure the speeds of gas particles. I won't go into those details because that'll be a long side story. When you do the science, when you perform the experiment, this is the graph that results. This is what nature decides, and we just have to listen to what she says. Think of this axis as not being so much probability. Think of this as the number of particles with speed x, okay? So this is number of particles. And here you can see a velocity of gas particles being measured in meters per second. So we're in nice MKS units. Also notice that this is a measurement for a particular species for diatomic oxygen at a temperature of 300 Kelvin, which is a little bit warmer than our bedrooms right now, but probably a temperature that you might find up in the exosphere of a planet. If all the gas particles were evenly distributed throughout the velocities, then the curve would look kind of like a straight line, which would mean you'd have equal numbers of particles traveling slow, equal number of particles traveling medium speeds, and equal number of particles traveling at high speeds. Obviously, that's not what nature decides to do. Nature smashes around those gas particles such that there is a mixture of speeds, but it kind of follows an asymmetrical bell curve. It's a unique probability distribution unique to gas particles. It's known as the Maxwell Boltzmann distribution. As an example of another type of probability distribution that you might have seen before, something that's a little more common, anyone who's spent some time in a classroom taking some tests has probably heard of the bell curve before, right? The bell curve is what's called a normal distribution, or in physics, we call it a Gaussian distribution. And a bell curve looks similar to Maxwell Boltzmann, but it's not the same. Let's find a nice picture. This is too techy for you guys. Let's find something a little less technical. Okay. This is what the standard bell curve looks like. And what's interesting about the bell curve as a probability distribution is lots of things in nature follow a bell curve. If we were to stand at the front door of CCRI and measure the heights of all the hundreds of students that walk through the door, we would discover that heights of human beings follow a bell curve. If we measured the scores of my students' exams for the last 10 years and put them all into a probability distribution, we would find that the students taking my exam follow a normal distribution. Lots of things in nature, for some reason, follow a bell curve. The Maxwell Boltzmann is a unique probability distribution that is not a bell curve. What makes it different can be seen right here. It's asymmetrical. You have a most probable speed, which we're going to call the thermal speed here. All right. But you also have the presence of this high-speed tail. And the high-speed tail means there's just a little more particles traveling at high velocities than there are slow velocities. And I think you guys could almost see that now that you know the answer. If you look here, let's add some heat. Oops, that's not what I want. Let's add a little bit of heat to these gas particles. It's almost as if you can see a few more of those high-speed particles than slower ones in this sped up animation here. Notice we've got a bit of thermal escape of gas particles leaking away. What's interesting about this and what's worth talking about is any of the particles in the high-speed tail, let's say this is your escape velocity, okay? Let's say this is where that's the escape velocity of your planet. Any particles which are here occupying the high-speed tail, they can jump off and leave to outer space because they're traveling faster than the escape velocity. But your curve will not simply look like this afterwards. What's going to happen is collisions will repopulate the high-speed tail again, and you'll have new particles which are capable of leaking into space. Let's try to draw that on the board because my computer art skills are not as good. So in a Maxwell Boltzmann distribution, you make a plot of the number of gas particles as a function of your velocity. This one we're going to do in kilometers per second, because in our class, we like to convert escape velocities and thermal speeds into kilometers per second. And you have a distribution that looks something like this with a sort of high-speed tail. Here is your escape velocity. These particles can leak into space. This speed here, the most probable speed, is what we call the thermal speed. For most gas particles, the thermal speed will be way lower than the escape velocity. So at first you'd think, well, most of the gas particles can't leak into space, so you're fine. But once again, the problem with having these particles leave into space is gases through collisions will reform a Maxwell Boltzmann velocity distribution. They have to do this. Nature makes it do this. So at first, your distribution looks like this, right? Because those particles have bled away into space. And then as the gas particles collide, they will reform a Maxwell distribution with slightly less area because there's less particles. And now new high-speed particles will form to leak away into space. Notice, for instance, that in the 5 or so minutes that I've been yapping about this stuff, we've actually considerably thinned out our gas in our animation because thermal escape has been kicking random particles off. If you don't replenish an atmosphere with volcanism, thermal escape will kind of chip it away, depending upon the temperature. I'm going to erase this. So the question is, how do I know if my planet will lose its atmospheric gas? The answer is you calculate the escape velocity, 2gm over the radius of the planet. Then you calculate the so-called thermal speed. We did this for our homework, and we're going to do it again. The thermal speed is the speed that the greatest number of particles have. I use V with a subscript THM for thermal. 2kT over the mass of the particle. I want to make sure that you guys understand something here. Do you guys understand the difference between this mass and this mass? Notice I used a lowercase m and a capital M. I don't know how much I need to explain that, but why don't you guys tell me if you know. Jenna, what's the big M? What's the little m?
I'm assuming the big M is the total mass and
Wait, total mass of what?
of the atmosphere.
No. Okay, I guess I do need to explain that. That's the mass of the planet. This is the mass of the gas particle. Remind yourself that in the thermal speed, K is the Boltzmann constant, 1.4 times 10 to the minus 23 joules per Kelvin. This is going to be important for anyone who decides to take my final exam. And it's important just to learn, I don't know, what planetary scientists do when they study atmospheres. Then you apply the test. And we've done this before. If the thermal speed is greater than or equal to 1/5 of the escape velocity, the gas is lost, not in one day, not in 1 week. The gas is lost over a geological time scale. Jenna, Orion, do you remember what a geological time scale is?
I'm thinking like the 1 centimeter per.
minute. Yep. Yeah, so how long does it take to reshape the continents on Earth?
100 million?
That's a pretty decent version. I just want to say that attendance is pretty bad today. I have 4 students here, and only 2 of them are sharing video. So that's to be expected. I know this happens over time. I thank you guys for being here. Today, since I'm not doing a lab, I'm committed to doing this whole lecture with you guys. But if it continues to be this bad next week, I might sick the pre-recordings on you. All right, we'll see what happens. But I hope I can get a few more people to attend the last 3 lectures we have. This is another reason why it's so important to have some projects and assignments for students. Otherwise, it's all too compelling to just check out of a class, you know? All right, that's just me bitching. Let's try a sample problem. Sample problems are good for you, especially if you end up deciding to take the exam. Obviously, the people who will be best suited to take the exam will be people like Jenna and the 2 Ryans and Valerie, who are here often. the people least suited to take the exam will be the ones who don't come to lecture. So it's a little bit of a warped scenario. Let's try this example to make sure you really understand it, because I would probably make you do this 2 times during the final exam. So just in case you're planning on doing that, it's fair. Obviously, humans need oxygen to breathe, correct? It might be of concern to us whether or not Earth can hold on to its planetary oxygen. What do you think the question is? Can Earth hold on to its atmospheric oxygen, yes or no?
Yes.
Otherwise, we'd be fucking dead by now, right? Okay. However, it could be a neat little sample problem to see what we can handle, all right? So, can Earth hold on to O2? And remember, it's in its exosphere. Now, I'm going to ask you guys a question that I think you know the answer to, but I want you to prove to me that you know the answer to it. It may not be as obvious as I think it should be. Here again is a diagram showing us the layers of Earth's atmosphere. Why am I only worried about thermal escape up here? I think I even talked about this before. This is the layer in which we have thermal escape. Why don't I worry about thermal escape in these layers?
Could it be that the exosphere is the very highest level of the atmosphere? So in order for it to reach thermal escape, it will have to be, it can't just start at, like, say, the troposphere, because that's where everything's kind of weighed down more, in a sense.
Okay, Ryan, you're not totally wrong, but you could be better. Jenna?
I was going to say something similar, but it's reproduced from the lower levels, so it's
You're s-
more.
You're still missing the key idea. Let's say I had a gas particle right here. On Earth, I happen to know the escape velocity is 11 kilometers per second. We've calculated that before, okay? If this gas particle was traveling at 11 kilometers per second, you learned in your lecture on Newtonian mechanics and gravity that anything traveling faster than 11 kilometers per second can escape the gravity of Earth, period. After all, Jenna, rockets travel to outer space from the ground, and they travel at 11 kilometers per second. However, a rocket is not a gas particle. If I had an oxygen molecule traveling at 11 kilometers per second right here, it would not achieve escape. Why not?
Because of our ozone?
Not exactly. Okay, if it was here, it wouldn't. And ozone isn't there. It's not about the ozone. Exactly. It's about, maybe you should look at the animation for inspiration. Let's add some more gas particles. Why are particles leaking away up here, but even the zippy ones aren't leaking away down there?
That's less dense of particles.
Yeah, so why does the density matter? The density does matter. Why?
Because the higher density of particles.
Boy, you need like a fancy freaking vocab term that you don't have right now. I think the vocab term that you wish you had, the science term, is called the mean free path. The mean free path is how far can a particle go before it collides with its brother or sister particles, right? What do you think the mean free path is up here? Well, I guess you won't have a number for me, but can I get a diagram of the mean free path? Okay, so flush this out for me. This is a concept from gas dynamics, from statistical mechanics. Here, this is perfect. You need this idea, the mean free path. Here, the mean free path is short. I can only travel probably in the case of gas particles, less than a micrometer, maybe even a nanometer or two before I collide with another particle. Actually, it's probably micrometers is what I'd guess. It's probably a millionth of a meter before it collides with another gas particle in the troposphere. By the time you get up to the exosphere, the mean free path could be a kilometer. All right, so just make sure that you understand. Make sure that you understand me here. Explain it to me. Once again, what's the real reason why particles can escape from the exosphere, but not the troposphere or the stratosphere, any of that stuff?
Because there's a lower density of particles, so they have a longer mean free path.
But and they can actually get into outer space before moshing. Here you're too deep in the mosh pit, right? That's the simple explanation. Here the mosh pit thins out, so you can get out of the mosh pit, all right? That's why the exosphere is where particles leak from. Also, what's happening to the temperature in the exosphere?
It's getting colder.
Oh my gosh.
It's
Look,
getting hotter.
look, yeah, if you go from -20 Celsius to 80 Celsius, right, it's getting hotter. Why is it getting hotter the further out into space you get?
Lack of,
No, just read the thing.
oh, it's heated by solar UV
And
X-rays.
and
The fast moving molecules
no,
create
no, not just that, but one other thing besides UV and X-rays are heating up the exosphere. Something from the sun that's not radiation.
light.
Radiation is light.
Would it be the solar winds?
The solar wind. The solar wind heats these gas particles as well. Very good. Okay. They say a typical, let's say the temperature in the exosphere is like 40 or 50 Celsius. We might actually want to try 300 Kelvin, but yeah, if it's 30 Celsius, that's pretty close to 300 Kelvin, right? So let's try our problem. So I'll save ourselves a bit of time here. From our chapter 4 lectures, the escape velocity of Earth is 11 kilometers per second. I could redo that, but I've already done that exercise in class, so I'll leave it there. If we have diatomic oxygen, the typical molecule of oxygen has 8 protons and 16 nucleons. And that means basically it's 16 times more massive than a proton, which of course is a basic protium hydrogen atom. Therefore, the mass of O2 is 16 times the mass of hydrogen. I don't memorize the mass of every gas particle. Oh, sorry. Is O2 16 times the mass of hydrogen? It's 32 times, because O2 is actually 2 oxygen atoms. So let me fix that up. A mass of a diatomic oxygen is 32 times the mass of hydrogen. I have memorized the mass of hydrogen as 1.6 times 10 to the negative 27 kilograms. Why don't you guys punch up and tell me what you get for your mass there?
I got 5 times 10 to the negative 26 kilograms.
Thank you. I like that you guys are instinctively using units now. That's nice. Okay. let's say that in the exosphere, just so we can compare it to our own graph, the temperature is 27 degrees Celsius or 300 Kelvin. We can now calculate the thermal speed as, this is the thermal speed of O2, by the way, 2 times 1.4 times 10 to the negative 23 joules per Kelvin times 300 Kelvin divided by 1.6 times 10 to the negative 27 kilograms. Why don't you punch that up for me? I wish I had actually done this problem for a water molecule, but that's okay. Water molecules are slightly less heavy than O2, but
So I got about 2,300, and for the units, I'm not confident. I know it's like joules over kilograms or
that actually sounds a bit. Oh, I'm sorry. Look, I used the mass of a hydrogen atom because I just did it instinctually. We should use the mass of O2, correct?
oh, okay, let me put that in.
That's my fault. That's my fault. What did you get the first time you got 2,300? Let's remember that. Ryan, are you punching this too? Since you're my other victim here, you need to work.
Yes, I am.
Thank you. Please practice. You're doing it. Oh, both Ryan. Right. I can kill two birds with one Ryan. That's what I can do here. Yes, Jen.
Okay.
Or anyone. I don't care who says it.
I can I got a.
Yeah.
Ah, crap. I hate when that happens. Hold on. I have to.
Jenna, what'd you get here? Because the clock's ticking.
I got about 400.
All right. Now we
Or-
got to talk units.
410.
Yeah, that's wrong.
All right. 410 what?
So I'm thinking it's joules over kilograms, but my gut says it's not right.
It's first of all, it's radical joules over kilograms. If you remember that kinetic energy is
Oh yeah, I was gonna say I forget what joules are. It's like broken into kilograms, and we cancel the kilogram.
so here's how I remember joules. I know the formula for kinetic energy, right, Jenna?
Uh-huh.
What are the units of mass times velocity squared? Mass has units of
Grams.
that's not MKS. You guys
Okay.
say MKS. Mass has units of
Kilogram.
right. What about velocity squared?
Mass. I don't know.
Velocity is meters per second.
Oh yeah. Yep.
So joules, that means radical kilograms times meters squared per second squared divided by kilograms. What's that reduced to?
Second squared divided by kilograms. Meters per second, because it's a velocity.
Right.
Yeah. I should have guessed that.
Right, you should have. That's okay though. Okay, so how many kilometers per second is that? Let's do dimensional analysis.
Is it 41000?
No, give me units, top and bottom.
Meters on the bottom, kilometers on top.
What's the conversion factor? Oops, sorry, that's kilometers. What's the conversion factor?
I always forget. Is it 1000? No, it's 1 on top and 1000 on the bottom.
Yep.
All right.
Okay, so if you divide by 1,000, you move the decimal place 3 to the left.
Yeah, so it'll be 0.4 kilometers.
Okay. Now what we're going to do is we're going to apply the test, okay? 1/5 of the escape velocity is 1/5 of 11 kilometers per second. What's that?
$2.2.
Okay. Can Earth hold on to its planetary oxygen, Ryan?
Yes.
Yes. Because this number is way lower than that one, right? Earth easily holds diatomic oxygen. That's good for us. That means our oxygen isn't going to boil away into space. On the other hand, remember, Jenna, that when we first tried to do this problem, we actually did ourselves a cute little favor. I accidentally wrote down the mass of a hydrogen atom, and you correctly computed it as 2,300. What are the units again?
Meters per second.
How many kilometers per second is that?
2.3.
Can Earth hold on to
No.
hydrogen? Isn't that interesting? This is what, do you want to know what Earth would look like if it had been a little bit more massive, my friends? Let me show you what Earth could have looked like. Ever see this guy before? This could have easily been Earth if Earth had formed just a tiny bit more massive. Because in the early solar system, which, damn it, I forgot to cue up that slideshow. Remember, the early solar system formed from a protosolar nebula. And the gases that condensed onto the planets were both, let's just look at a picture of a planet forming here. I have a crappy little picture. Here we go. I love this illustration because it kind of shows a whole bunch of things at once. When Earth, oh shoot. When Earth first formed from the protosolar nebula, this is probably what it looked like. There was probably a bunch of hydrogen and helium gas with a bit of grit sort of along with it, and Earth was sort of condensing through collisions and gravity to pull all that nearby material down on top of it. But the lump that originally formed Earth did not have a large enough mass to radius ratio for it to capture primordial hydrogen. Remember, the Earth would have been hot too, so it would have been easy for hydrogen and helium to just boil off into space. Farther out into the solar system, temperatures were colder, number one, but there are also some other issues that I'll get to later involving the frost line, which explain how Jupiter and Saturn ended up massive enough to capture some of that stuff. Earth cannot hold on to hydrogen. It can hold on to oxygen because oxygen is 32 times more massive and therefore 32 times more sluggish. Can I show you one more example of this? Sure. Let's look at differences in the thermal escape between two different species in my crummy little animation here, right? All right, so let's add some heat. Notice that as I Wow, sorry, we had boiled ourselves down to 5 Kelvin there, right? But now I'm adding some heat and you can see lots of thermal escape happening, right? Come on. It's hard to add heat when you don't have a lot of gas. Let's add some heavier species now. Notice that the more sluggish species are held, sorry, I just gave a little jolt, but the more sluggish the gases are, the more they're kind of hovering down at the lower gravity of the planet. If I add even more gravity, forget about it. Those heavier species can't really escape so well. You'll still have the occasional particle boil off into space, but it's rarer. Okay, I want to do a couple more things before we end our lecture today. I want to talk about the role that magnetic fields play. I want to take you guys through a history of the different planets' atmospheric formation. And I'd also like to talk about just what it might be like to travel through the atmosphere of Earth. I don't think I ever put these down as formal notes. I talked about them during one of our homework sessions, but this is kind of important. There are two conditions for a planetary magnetic field. The first is a hot interior, and it probably will include a partially liquid metal core. Probably a liquid metal core gets warm enough to ionize and create some ions. The second is a rapid rotation. And that's because I told you before that a magnetic field on a planet is quite similar in most respects to a child's toy called an electromagnet. Maybe an advanced child's toy. Okay. A reminder of the electromagnet and how that works. You take a thin loop of wire, you send a current through the loop of wire, and it generates a small dipole magnetic field. The small wimpy magnetic field will cause the iron to become magnetized. Let's pick a direction here. So here, all of the iron lumps become magnetized in some direction. They then add to the magnetic field, making a really powerful dipole. This is a nice analogy, of course, because the interiors of the terrestrial planets are made of iron. So if we could draw a picture of this, here's your planet. Somewhere in the core, we have some hot glowing metal. The hot glowing metal with a lump of iron around it creates a bunch of ionized charges. You kick some electrons off. Then you add a fast rotation period. It seems that 24 hours is sufficient to be rapid rotation. And those charges going around form a kind of current loop. And you generate a magnetic field. Earth has a hot interior, a 24-hour rotation, so we get a magnetic field. Venus has a hot interior, but essentially no rotation, As a result, Venus lacks a magnetic field. Mars has a cold interior. It has the same rotation as Earth, 24 hours. Does it have a magnetic field?
Yes.
No, because it's cold. Its interior has cooled too much for Mars to have a magnetic field. However, we've studied the surface rocks of Mars and find that if you go back far enough in time, maybe billions of years, Mars at one point had a warmer interior and it did have a magnetic field in the past. Today it does not. What about the moon? Would the moon have a magnetic field?
No,
Why not?
it would not.
Why not, Ryan?
Because the interior of the moon is a lot colder. It's basically
Frozen out.
just all lithosphere right to the
Yeah,
core.
nice use of your vocab right now. You're talking like an educated person, and I like the sound of your voice. Mars is all lithosphere. It's frozen out. Very good. How about Mercury? Rotation of Mercury isn't very speedy. It's kind of locked in a gravitational resonance with the sun. It's it's not as slow as Venus, but it's like 20 or 30 days or something.
Then I'd say no, it doesn't, because it has a lack of rotation.
It doesn't have a complete lack of rotation. It does rotate a bit. Here's the weird thing about Mercury, Jenna. Mercury is kind of cold and it doesn't rotate super fast, but Mercury is almost an exception to the rule. And the reason why has to do with its core. Look at the size of its metal core in relationship to the rest of the planet. Unlike the moon, which has a lack of metals in it, Mercury just has a awkwardly huge metal core. Notice that its metal core is close to the size of Earth's, despite being a third its diameter. Because of this, Mercury has a weak magnetic field. It's not as strong as Earth's by any mean. It's hundreds of times less, but it's still significant enough to do some cool solar system physics. Now, I'm not going to get into Mercury's magnetosphere because that's a topic for a graduate course. But I did want to explain that Mercury's kind of a freak in terms of magnetic fields. I think for the purposes of our class, Earth is really the only terrestrial planet that has a magnetic field. But I feel compelled to mention that people do study Mercury's magnetic field because it's the only other terrestrial that kind of has one. It's just a lot wimpier. I want you guys to remember why these magnetic fields are so important in atmospheric science. They help protect especially water molecules from being lost on a planet. And let's remember the story that happened on Earth, Venus, and Mars. Maybe we could even take some quick notes on them. On Earth, volcanism produces water, carbon dioxide, and other elements. But the water is at the right temperature and pressure under our atmosphere where it can condense through rain into liquid oceans that build up over time. So just as atmospheres are created by volcanism, we believe that oceans are created by volcanism as well. These oceans, of course, can trap CO2 on the seafloor bed in the form of carbonate rock, and that tends to have a well-balanced temperature mechanism where the small quantity of CO2 creates a very wimpy but useful greenhouse effect. On Venus, things got a little buggy for a couple of reasons. And we've talked about this before, but I want to go over it again. Venus was a little too hot for its water to condense into liquid oceans. So most of the water coming from Venus's volcanoes would have been in the form of steam. Now, Venus normally would be able to hold on to its water because water, like diatomic oxygen, is a heavy molecule, and a big old planet like Venus should easily be able to trap it. But now Venus's lack of magnetic field comes into play. because those high-speed protons from the sun will crash into water molecules in the upper atmosphere, and they will knock the hydrogens right off of the oxygen. Hydrogens can then thermally escape into space, and the resulting OH ions combine with sulfur to form those hydrosulfuric acid clouds. That's the stuff that dissolves spacecraft when we try to land it there. A lack of magnetic field on Venus contributed to its buildup of CO2 and its runaway greenhouse effect. That plus a little bit of extra high temperatures. Mars, on the other hand, probably suffered a similar fate. Did Mars once have water at its surface?
Yes.
And let's think about what happened to how climate change on Mars took place. So first, Mars as a planet is smaller than Earth or Venus. And that leads to a cooled interior. As Ryan pointed out, this leads to a thick lithosphere. I can think of two effects that result from that. This leads to a loss of volcanism. Also to a loss of magnetic field, which is very bad for your planet. The loss of volcanism leads to a thinner atmosphere and a lower pressure. What effect does lower pressure have on the once liquid lakes and rivers of Mars? When you reduce the pressure on the planet, what effect does that have on the liquid water?
Turn to a gas, so evaporate.
Evaporation, correct. Very good. A nice use of your terms that you've learned today. So now, on Mars, the volcanoes have dried up. You've got a bunch of H2O now in the atmosphere, the thinned atmosphere in the form of Venus. Now tell me, students, what will happen as the solar wind ions start colliding with these water molecules?
It turns into carbon clouds.
No, not carbon clouds. You're going to you're going to dissociate the molecules. These aren't photons, they're particles, right? What do you get when you bash apart water molecules?
It'll fall apart
It'll fall apart into what constituents?
into O2, into
Yes, keep going.
the O2 and hydrogen.
Okay, very good about O2 and hydrogen. O2, because the leftover oxygens, they're too heavy to thermally escape. So they'll combine O2. The hydrogens, however, if Earth can't hold on to hydrogen, can Mars hold on to hydrogen? No way. So all of those hydrogen ions will quickly thermally escape to space. What do the O2 molecules do?
Is that when they form the clouds?
Not
Carbon.
clouds. There are no O2 clouds on Mars. Mars's atmosphere, if you remember its composition, is 0% diatomic oxygen. Let's just take a look at that again, Jenna. The composition of Mars's atmosphere is 96% carbon dioxide, 3% nitrogen, 2% argon. There's no oxygen there. What happened to the oxygen? what does oxygen do to metals on Earth? So here's the ground, and let's say there's some iron and rock.
Oh, so it's the chemical reaction. The
Yes.
O2 causes the
O2
rust.
comes down to the surface, and what color is rust?
Red, reddish.
Right. So what this says to me, Jenna, is when we look at the surface of Mars today, I mean, just look. I have this here. Wait, this is atmospheres. Sorry. This isn't even the best picture I could find. Here's some pictures of the surface of Mars. Look at the color of all the Martian sand, the Martian surface, right? Everywhere you go, the entire surface of the planet is bloody red. I mean, even if you look at a global picture of Mars, with the exception of the ice caps, let's get a nice high resolution image here. The entire surface is red. And in a way, when we're looking at that, when we're looking at that completely red surface, what you're seeing there is all of the liquid water that once covered the surface in those oceans. The fossil record of that liquid water is there in the rusted red soil. All of that oxygen came from the stuff that we've been studying today. The break apart of those water molecules through solar wind ions, the escape of hydrogens, the chemical reaction of the surface. This tells the whole story of what happened to Mars. It makes you realize how important Earth's magnetosphere is. Our magnetosphere is a magnetic bubble that protects our planet from the harassment that solar wind ions must eventually cause. Our magnetic field constantly sloughs charged particles off into the side, kind of like a magnetic force field. It is a force field shield, right? It's electromagnetism ricocheting those charged particles off into outer space. Probably a magnetic field is necessary for life because otherwise your atmosphere will get all messed up over time, especially if you were to live around a star that had even more particle radiation than our own sun does. I wanted to do some other fun stuff with you guys, but let me check my time here. I'm a little bit over my budget, so I'm going to stop there. I hope that made a compelling story for what happened to climate change on Mars. Some technical stuff today, but that's necessary too. In our next class, we'll kind of get started on the Jovians, and we're going to do the Jovian homework next time. Actually, no. You know what we're going to do on Wednesday's class? We're going to do a hybrid homework. That should actually be in our, so you're not going to have lab today. I'm sure everyone's sorely disappointed by that, all 4 students that showed up. Okay, but on the class on Wednesday, the homework that I would like us to do is going to be a special homework not listed here. It's going to be a hybrid of questions from chapter 9 and 10 that we didn't do. I have them hidden somewhere. I'll find them for you and show them to you on Wednesday, okay? And then we'll do this, since most of you won't take the test, next week we'll do our final lab on the rotation of Jupiter, and this will be our final week's homework. That'll actually end up being homework number 12. So that's our rough game plan, okay? All right. Okay, guys, I'll see you on Wednesday. Enjoy the rest of your day. Catch up on work if you've got to, all right?
Have a good day.
You too. Bye-bye.